So today we're going to look at solving some recurrence relations. So what's a recurrence relation? Well, a recurrence relation is where a sequence is defined in terms of terms that came before it. The first example I've got here is my recurrence relation of the form a sub n is equal to a sub n minus 1 times n. And n is allowed to take on values 2, 3, 4, 5, 6, dot, dot, dot. Now, that in and of itself would not give us a sequence. We have to give what's called initial conditions. So the initial conditions I have today are a sub 1 is equal to 3. So that gives the first term. So a1 is 3. Now today we're going to solve these recurrence relations by iteration. And by solve, I mean we're going to find a function without ellipses that tells you what every value happens to be. In this case, we start with a1 is equal to 3, and then we iterate on it. Now to do that, we do a sub 2, and then a sub 3, and then a sub 4, etc. And we keep going, simplifying very little, grouping terms together that come from the same part of the equation, and then eventually, hopefully, we find a pattern. So let's start out with a sub 1 is 3, then a sub 2. If you go back up here to our equivalence relation, a sub 2 is 2 times a sub 1. So that turns out to be 2 times 3. So a sub 2 is 2 times 3. Now, of course, we know that's 6, but we don't want to simplify that much because that's going to hide the pattern. Now let's go to a sub 3. Well, a sub 3 is 3 times a sub 2, which is going to be 3 times, and then a sub 2 is 2 times a sub 3. Now what I want to do is I want to group the terms that come from the same piece of the equation. And the terms that come from the same piece of the equation are 2 times 3. They both come from this part of the equation, n. Now what's left is just this number 3. Okay, so I'm going to group a sub 3 as the quantity 2 times 3 times 3. Now I'm going to go on to a sub 4. A sub 4, by our definition again, is what? 4 times a sub 3. So that's equal to 4 times, and then a sub 3 is 2 times 3 times 3. Again, I'm going to group the terms that come from the same piece of the recurrence relation, that come from n. And those numbers are 2 times 3 times 4. So I group those together and I see a sub 4 is 2 times 3 times 4 times 3. Now I'm starting to think that 3 on the far side just goes along for the ride. And I'm trying to think, what's the relationship between that index and that term, 2 times 3 times 4? Well, I go on to a sub 5, and a sub 5 is 5 times a sub 4, which turns out to be 5 times 2 times 3 times 4 times 3. Again, I group the terms together that come from the same piece, and so that's 2 times 3 times 4 times 5 times my 3 that's left over. And then I think a sub 5 is 2 times 3 times 4 times 5. What's that? Well, that's 5 factorial times this 3. And then I look back at all my other terms. A sub 4, that's 3 times 4 factorial when you look up here. A sub 3 is 3 times 3 factorial. A sub 2 Well, that could be thought of as 2 or 3 times 2 factorial. After I look at that for a while, I decide that my general formula for a sub n is 3 times n factorial. Notice that my original recurrence relation was good for n element of the set 2, 3, 4, ... But my final answer is good for n element of the natural numbers, and the natural numbers, of course, are 1, 2, 3, 4, etc. So just to remind you, the natural numbers are 1, 2, 3, ... and keep going. So that's my final solution.